let's assume that we have a pipe here, where at point 0, let's assume that we have a solid things like a solid object like a stone. Now, let's put a stone here. If we open the pipe, the water must go directly down to the table where there is an object. Let's assume that this screen is a free screen. There's not any disturbance between contaction of water and the fluid. It's a free screen. So this water must go like this. In fluid we use fins. If the water contacts with the object here, this one must turn to this side, and this one must turn to this side. So, everywhere, because you are busy conducting a magnetohydrodynamic problem, if there's a movement of particles inside the fluid, there's a particles. Where there's flow, there's a particles inside. And that particle generates, sometimes you can generate electricity using magnetohydrodynamic flow. Sometimes you can generate electricity. You can generate using water, hydro water electricity. So look like the fluid is going directly to the surface. After contacting with this object, the fluid turns like this opposite direction. So this point where there's contaction, I'm already defining it. It's called a stagnation point. Yeah. Velocity here is 0. After turning opposite, the velocity continues to increase. Okay. So, because inside the fluid there's a particles, moving particles, we can assume that there is some magnetic, because the water is going down, there is some magnetic going up. That magnetic is called magnetic field intensity. Magnetic field intensity, which is denoted by this here. This magnetic field intensity is perpendicular to the surface where there is a stretching sheet. So this form of magnetic you can't see by eyes, but this we call it is a linear. This magnetic field is linear, like a loop. Is in linear. So we define how the fluid flows through our model, how to conduct, how to put a stretching sheet, how to put objects so that can block the fluid so that we can easily to understand the problem graphically. So where there is sheet here on top of surface, there is a temperature, like before. I said there's a temperature inside and temperature outside. Where there is there's a temperature, we denote this temperature on the wall. This W we can say temperature on the wall, but somewhere there's another temperature. We don't know about it. It's temperature away the wall, where the model conducted. There's a temperature in the wall, then temperature away from the wall. So these temperatures are different. if you see. This one is unknown. It's any number, because depending on the people, how people behave. How people behave, like I said before. It's affected due to climate change or many aspects from people. Talking too much. So, this is how this problem conducted graphically. So, in order to avoid the affection on the free stream, we ignore the polarization of charges and Hall effects, so that what we want to avoid the migration of particles or the migration of charges from one place to another, so that we can conduct this model easier. Okay, it's okay now. Let's go to method of solution. Method of solution is difficult to choose method if you are a mathematician. But firstly, try to understand why and what can I do if I choose this method. So I choose this method because it's easy to understand in terms of other methods. So this method is called spectral relaxation method. So that then before, if you choose this method, you can understand more mathematically or numerically. You can play around this problem mathematically or numerically if you want. So firstly, before I go deeper to the summary of this spectral method, I'm reminding you what's the meaning of boundary value problem. A boundary value problem are those problems which is like if you want to see the difference between the partial differential equation, you must check how many terms you have so that you can see it's a boundary or a boundary problem. There's a boundaries and boundary problem. But when you call the equation is call it a boundary